Section 15.7, Pascal's triangle. And the binomial theorem. Okay, so first off, let me recall Pascal's triangle. And so, let me put a 1 here. Now, I drop down the 1's, and that gives me the second row. Now, drop down a 1. I add the 2 above. 1 plus 1 is 2. Drop down the 1. Next, drop down the 1. I add 1 plus 2 is 3. 2 plus 1 is 3. Drop down the 1. Let's look at the binomial expansion. These are the special product formulas. So, x plus y to the 0 is just 1. X plus y to the 1 is just x plus y. X plus y squared is x squared plus 2xy plus y squared x plus y cubed is x cubed plus 3xy squared plus, I should have written it the other way, plus 3x squared y plus 3xy squared plus y cubed. Okay? So now notice the following. If I write it as follows, well, this is the same as x to the first, y to the 0. This is the same as, well, let me put a 1 in front. So 1 x to the first, y to the 0, a 1 x to the 0, y to the first, a 1 x to the 0, y to the 0, a 1 x squared, y to the 0, 2 x to the first, y to the first, plus 1 x to the 0, y to the 2, a 1 x cubed, y to the 0, a 3xy, x squared, y to the first, a 3x to the first, y squared, a 1x to the 0, y cubed. Okay, so now if I look here, the 1, 1, 1, oops, 1, 2, 1, the coefficients of these binomial expansions are the same as the coefficients, the number in Pascal's triangle. And so, if you notice that, the Pascal's triangle give the coefficients of the binomial expansion. And in addition to that, notice for the x's, if I add 0 plus 0, I get 0. 1 plus 0, 0 plus 1, I get 1. 2 plus 0, 2. 1 plus 1, 2. 0 plus 2, 2. 3 plus 0, 3. 2 plus 1, 3. 1 plus 2, 3. 0 plus 3, 3. And so I notice that the sum of the exponents are always the power in the binomial expansion. And notice that the exponents of x go from 3 to 2 to 1 to 0. For y, 0 to 1 to 2 to 3. So they're always, for x is going down, for y is going up. Sort of, not really. But yes, they're, in this case, they are just the coefficients of the binomial expansion. Okay, so if I expand one more, let's say 1, 4, 6, 4, 1, I could then say that, well, x plus y to the fourth must be, well, there's a 1 here, so there'll be a 1, x to the fourth, y to the 0, plus, there's a 4 here, so 4, x to the 3, y to the 1, plus there's a 6 here, 6, x squared, y squared, plus there's a 4, x to the first, y cube, and lastly there's a 1, x to the 0, y to the 4. And so I have determined a new special product formula just by looking at Pascal's triangle. So you actually don't even have to have memorized any of those special products formulas that involve the perfect trinomial, a perfect square trinomial, a perfect cube. They're actually all part of this idea of Pascal's triangle. What page? What page is it? It's chapter, so the visual, there it is. This is page 675. If you look at page 675, the very first page on the section in Pascal's triangle. Okay. Let okay. Okay. Next, let's look at factorial. Okay, so 4 factorial is just equal to 4 times 3 times 2 times 1. So this little exclamation point denotes the idea of a factorial. And for a factorial, you just start with your number and keep going down till you get to 1. Okay, so this is equal to 24. So you just start at that whole number value and keep multiplying by each of the preceding whole number values. So let's say I look at 6 factorial. It would be 6 times 5 times 4 times 3 times 2 times 1. I will tell you how that it is related, yes. Okay? And so, this is going to be 720. So if you just multiply all those together, you should get 720. So I can define factorial as follows. Let n be any natural number. Then I'll define 0 factorial as 1. I'll define n factorial as equaling n times n minus 1 factorial. Okay. If I do that, then I can see that, well, 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. 2 factorial is 1 times 0 factorial, which is 1. And so 4 factorial is just 4 times 3 times 2 times 1, using that definition. Okay. Of the factorial. So that's how I can define factorial. Well, that's what it means to does it always have to be a formula? No, it can be a concept, but that's more advanced. Okay. And so, on your calculator, there is a factorial button. And so, say if you wanted to figure out a factorial, you would just find your, well, usually you put in 8, and then you click on the factorial, and you can calculate 8 factorial. If you do that, you would get 40,320. It looks like an exclamation. It's the exclamation point. So either it will look like an exclamation point, or it will look like X exclamation. It depends what type of calculator you have, where exactly it will be located. Okay. So, binomial coefficient. And so, the binomial coefficient is denoted as follows. It's just, well, maybe I'll redo this again. It's just a number floating above another number in a parentheses. So notice that I don't, it really is a number floating above another number. There's no, and then I just put it in a parentheses. And that is the notation for the binomial coefficient. Sometimes we denote this by the following notation in CR. We usually don't, well, that is actually the notation that you will get when you take your a course in statistics. So this is actually not a mathematical notation, but it's a notation from statistics. Okay. The way we define the binomial coefficient is in terms of factorial. It's n factorial over r factorial n minus r factorial. And that's the definition of the binomial coefficient. So let's calculate, let's say 8c2 is just equal to 8 factorial over 2 factorial times 8 minus 2 factorial. So let's calculate each of these. What is the question? I want to calculate, evaluate this number. So this is equal to 8 factorial over 2 factorial times 6 factorial. And so 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 6 factorial 6. 5 times 4 times 3 times 2 times 1. But you notice 1s, 2s, 3s, 4s, 5s, 6s cancel. So there's a whole bunch of cancellation. 8 divided by 2 is 4, times 7 is 28. And so we have that 8C2 is 28. If I calculated, yes, but it's easier. Notice it's much easier to do 4 times 7 than it is 4 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Calculate that, then do 2 times 1. Calculate that, then calculate 6 times 5 times 4 times 3 times 2 times 1. Calculate that, multiply the 2 factorial times 6 factorial, and then divide the 8 factorial by 2 factorial times 6 factorial. It's much easier to just cancel. Then all you have to do is 4 times 7. It's a much smaller calculation. Okay. Of course, on a calculator, you can do it, but, much smaller numbers. Okay. So, what you notice is that, let's have 12 factorial. Let's do 12C4. So let's calculate that. You can also do this on your calculator if you want. On a calculator, you would just, in the same location that you found the factorial button, you will find the NCR button is located in probably the exact same location, just next to the factorial button. I will give this to you in a second. What I'll say is that in real world, if you do things in statistics, there's a whole chapter on this. So I'm not going to really go over this. They'll go over it in statistics. This is how you you would use it when you calculate probabilities. This is the number in statistics. This will be the number of combinations. Okay, so this gives you the number of combinations of to choose R objects out of N objects. Okay, so we'll not be doing that, but in your statistics course you will be doing that. Okay, so if you plug that into your calculator, you'll get 495, or what you can notice is the following. So let me do this by hand rather than doing it on a calculator. No, factorial is a number. It's like saying 8 times 3, it's some sort of mathematical operation. So it's a mathematical operation, and from this mathematical operation, you come out with a number. Okay? We use factorial. I haven't told you anything about the binomial expansion yet. So I will in a few minutes. So I will be telling you about that. Okay, so this is equal to 12 factorial over 4 factorial times 12 minus 4 factorial. Okay, so this is 12 factorial over 4 factorial times 8 factorial. So now let's do this calculation as before. Four factorial is 4 factorial. And so let's calculate both 12 factorial, 4 factorial, and 8 factorial. So 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6, 5 times 4 times 3 times 2 times 1. Okay, let me calculate. Let me write down this calculation. 4 times 3 times 2 times 1 times 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Yeah, so this is 12 factorial divided by the quantity 4 factorial times 8 factorial. Now notice the 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s all cancel. Just like before, notice that the 6 factorials canceled. So notice in here, I only had really the product of two numbers. And this was 8C2. Here, all these canceled. So really I have just the product of four numbers, 12C4. And so now notice 12 divided by 12 is 1. 10 divided by 2 is 5 times 9. 45 times 11 is 495. And that's what we got from before. But notice this is a much nicer number. So now, I never had 12 factorial over 4 factorial. I had 12 factorial over 4 factorial times 12 minus 4, which is 8 factorial. Okay? So notice this. So look at this. That is 12C4. That's the definition. Okay? Evaluate. The question is to evaluate. It's like when I tell you 4 times 3 is equal to, that is telling you to multiply, to evaluate. Okay? Okay, so now, notice I could have also said the following. So I could have said, notice that it's 12C4. I want to, yes. Why? Uh-oh. Why did you say 1? Why did I say 1? Oh, this is probably what it is. 12 divided by 12 is 1. The 12s cancel. Okay, so now let's look at this. And so let's calculate 12C4. And so to calculate this, notice all I need write out is the first 4 terms, because these would always cancel. And then you divide by, so notice it says 12, so you start at 12. It has a 4 here, so you write out 4 terms. Then you divide by the 4 factorial. Notice you have the same number of terms in both the numerator and the denominator. How do I see the question? 8 times. It's so 8 times 8 is equal to 64. That's how you would, if you want to multiply 8 times 8, you get that 8 times 8 is 64. How do you state a factorial statement? Question. I don't know what you're asking. And so, how do I state a factorial question? How do I know what the question is saying? Are you asking if I do to calculate 5 factorial? Again, if I wanted to, okay, look, if I say what is 1 plus 1, okay, then the question would be evaluate 1 plus 1. 1 plus 1 equals 2. Okay? Now, if I said what is 2 factorial, 2 factorial is, so we would say evaluate, calculate, simplify. What is the number? 2 times 1 is 2. How do I say 12 over 4 in factorial? That makes no sense. 12 over 4 in factorial, I have no idea. 12 over 4 in factorial doesn't make any sense. That is not a sensible question. I have no idea. Well, I don't know. That doesn't make any sense at all. 12 over 4 in factorial makes no sense. I don't know what you're talking about. Okay. Oh, are you saying this? Are you saying determine, are you saying to evaluate that number? Yes. Well, okay. Evaluate the number. Such as when you ask, what is 1 plus 1 equal to? It's the same question. 2. Okay. 495. Okay. Right? You're doing a calculation. So calculate that number. Okay, so let me do this again. Let me do this because we again have gone off topic and no one knows what the original question is. Okay, so let me do. Okay, let me. What is the left side? I do not understand what is on the left side of the equal sign. It is the binomial coefficient. Okay, and so the binomial coefficient. Yes, and so the binomial coefficient to calculate 12C4, we do the following. We start at the number 12. We then write out the next 4 numbers. 12 times 11 times 10 times 9. 4 numbers because that is a 4. 12 because this number is 12. That's what we start out with. Next, we divide by 4 factorial because that's the number 4. And so, that's all you have to do. Notice 12 divided by 12 is 1. 10 divided by 2 is 5 times 9 is 45 times 11 is 495. So this is the only calculation you need do if you do not have a calculator. Twelve factorial is 12 times 11 times 10 times 9 multiplied out all the way down to 1. 4 factorial is 4 times 3 times 2 times 1. Yes. Okay, so because remember, these always cancel out. So we noticed, so that was the thing that we noticed. We noticed that the 8 factorials canceled, just like the 6 factorial canceled. Therefore, the n minus r factorials will also always cancel. Therefore, and this is what I want to get to, I can define the binomial coefficient as follows. Let me write the definition. Let me write the definition. So the binomial coefficient, I can define it as n times n minus 1 times n minus 2, and I'll keep multiplying out till I have r of these over r factorial. And I can define this for r being any whole number and n being anything. It can be any real number. Here, wait 1 second. Yes, so that is correct. This binomial coefficient can be calculated just by this calculation. And so I can define my binomial coefficient as above. Okay, good. So now, next, let's note the following. The binomial coefficient is the value in Pascal's triangle for the corresponding row and column. So let's do that. Yes, so this formula is the definition of the binomial coefficient. It extends the definition of binomial coefficient for the above case that I gave. Now I can actually do it for real numbers. And what is n? So n is any real number. R is any whole number. So let's calculate. Oh, let's say, I don't know how far I went. I probably did 3c2. Let's calculate this using Pascal's triangle. So let's use Pascal's triangle. To calculate the following value. Let's say C3. Oh no, I can go up to 4. 4C2. Let's calculate that. No, you actually don't say that. If you notice, when I write it, I say NCR. So notice I keep saying C. So we actually, even though we don't use this notation, we actually say the notation. So when I write the 12 hovering over the 4 in parentheses, I actually say 12C4. So notice I'm actually even though I'm not using the notation that they have in statistics, we actually just say the notation. We say it's a binomial coefficient of 12 and 4. Or we say it's the 12C4. Okay, so now let's compute 4C2. And so to do that, let's go up here to Pascal's triangle. And so I want to do 4. So now what I do here is that n will be the n that I have in the binomial coefficient can be found by looking in this at the rows, and the columns will give me my r. So I want to do 4c2, and so the thing above 4 I find by first counting starting at 0. So 0, 1, 2, 3, 4. So now I'm at the correct row. So this 4 here gave me my column. So the column is 4, counting. So I start counting at 0. Meaning it's really the fifth column. It's the fifth row. I'm sorry, I said column. The row is 4. And so you start counting at 0, meaning it's the fifth row. Fifth row. Next, the column can be found by the number 2. But again, you start counting at 0. And so that'll mean it will be the third column. Okay? No. C is, again, it's not, the meaning of that is combination. It comes from a notation in statistics. We're not doing statistics. That's just the name we give it because that's the name they give in statistics. It means combination. Okay? But again, it's the notation they use in statistics. Okay, so now let's do the row. And so let's do the R. And so I have N is 4 and R is 2. So 0, 1, 2. Therefore, I have that 4c2 is equal to 6. And so if I calculated that using my calculator or whatever, I'd get the same answer. Okay? Or any of the above techniques I gave you for calculating 4c2. Okay, so let me give you so it would be NCR. So this is 4c2. Okay, so let me give you the binomial theorem. Why 6 and not 12? Because if I look here, the number is 6. Okay? And so I found that the row corresponding to n equaling 4 and the column corresponding to r equaling 2 gave me a value of 6. Therefore, 4c2 has a value of 6. Okay, so let me give you the notation, the thing that we noted above. Well, that's only, well, you don't have to memorize. I mean, the Pascal's triangle has easy calculations. Notice we calculated from before, but Pascal's triangle, you always have ones at the end, and to find the next element, you just add the 2 above, and that gives you the elements in Pascal's triangle. But we can either use Pascal's triangle, or we can use, well, the binomial theorem, and that's what I'm going to give you right now. And so the binomial theorem, or or you can use the definition for the binomial coefficient in terms of factorial, or in terms of this simplifying calculation. Okay, so let me give you the binomial theorem, which relates the binomial expansion to this idea that we had from Pascal's triangle, and the correspondence between the binomial coefficients and Pascal's triangle. And so the binomial theorem says the following. So first, let n be some whole number, okay, and then I have that x plus y to the power n is just the sum r equaling 0 to n of NCR x to the power n minus r y to the r. Here I'm going to make the assumption that 0 to the 0 is equal to 0 or equal to 1, whichever works so that this expansion makes sense. So it comes out to the correct answer. 2 times 1 is 2. Oh, okay. Okay, so let's do, you're trying to do this calculation. I think that's what you're trying to do. 4C2. Okay, so, and then I'll finish off what I'm telling you about the binomial theorem. Okay, so now 4C2 is, you start with 4 and you write the next two numbers, 4 times 3, then you divide by 2 factorial. And so 12 divided by 2 is 6. And so you get the same number. Okay? Okay, so good. Yes, 4 factorial is 24. Okay, so leave off 3 and 2 on top. Leave off 2 and 1. Yes. Remember, this was right here, the simplifying formula for calculating the binomial coefficient. Or you could also, okay, so you could also, let me finish. Okay, let me do this and listen. Remember, listen. So this is equal to 4 over 2 is 4 factorial over 2 factorial times 4 minus 2, which is 2 factorial. And so 24 divided by 4 is again 6. Okay? So remember, you had 2 different ways of calculating it. And so this is the first way of calculating it. Here's the second way of calculating it. And then the third way of calculating it was using Pascal's triangle. Yes. Yes, okay. But remember, there were 3 different ways that we calculated. Okay. And so please note that when you when you have the binomial theorem, when you use the binomial theorem in statistics, uh, you will actually, they write this the other way around. They write this as x to the r and y to the n minus r. But again, you'll get the same expansion because, well, Pascal's triangle is symmetric. So it doesn't matter uh, if you do your expansion, going this way or going the other way. And so notice that these are symmetric. That Therefore, either way that you write it will give you the same answer. Okay. So now, I can also give you the following binomial theorem. Which says that if n is a real number, and again, I'll either have 0 to 0 equaling 0 or 1, so that the trivial cases work. I have that x plus y to the n is equal to the sum r equaling 0 to infinity of NCR x to the n minus r y to the r. You start a triangle, always start Pascal's triangle with the 1 on top. So you always start here at the top and go down. So the smallest part and then go down. Okay? Never the other way around. Okay, so that's the binomial theorem. We'll actually prove the binomial theorem a little bit later, but let's do some problems first, and then we'll show that. Okay, so on page, let's say 692. Let me do problem number 1. A plus 2 to the 4. Right, so notice that they're actually the same theorem. If you look here, notice they look the same. Now, if I have a whole number, this is the usual way that you see the binomial expansion. But we can actually do a little bit better than that. We can write the binomial expansion for any real number. That'll be shown not today or in this class, but in the future. You can actually do it for any real number where we use this extended definition of the binomial coefficient. Notice that this extended definition can actually still be true for all real numbers. Therefore, I can write this one theorem actually encompasses this other theorem when n is a whole number. So this theorem here is not necessary. You really only need this theorem, but notice that when n is a whole number, they're actually only a finite number of terms. When once you go past n, all these terms will be 0. So you actually have to only do the expansion up to n, which is what we said here, if n is a whole number. Okay? That's right. And so this is a more general theorem than the one above. It always works, so if you only want to remember one version, just remember this version, even though we'll be using the one above. Okay, so let us do problem number 1 on page 692. In exercises 1 through 8, use Pascal's triangle to expand the binomial. So I'm going to be using Pascal's triangle here to expand the binomial. Well, it depends on what, so the binomial, you did these whenever, this is one of the special product formulas. We use the special product formula in many differing situations. It depends on what the particular problem is asking you. This is how to determine special product formulas for not only the case of 2 and 3, which is what we did back in chapter 4, I believe, or 5, but to do it for anything in general. Okay, so in exercises 1 through 8, use Pascal's triangle to expand the binomial. So let's do that. Okay, so, well, this says this is equal to, well, the first number in Pascal's triangle. Well, to figure out, actually, we actually did it up here. To figure out that, well, notice that Pascal's triangle looks like 1, 4, 6, 4, 1 when n is 4. So when n is 4, I just use this column, this row. So let me write that row down. So for Pascal's triangle, I had 1, 4, 6, 4, 1. So those will give me the coefficients. You are solving. I'm writing an expansion. I'm expanding a binomial. Okay, so let's expand the binomial. Simplify. Another way of saying expand the binomial is simplify. Let's simplify. Okay, so the coefficient is 1. A to the, well, the power here is 4. 2 to the 0 plus the next coefficient is 4. A to the 3. 2 to the 1. So notice I start out with the power 4, then I go 3, and I keep going down. 4 plus 0 is 4. 3 plus 1 is 4. Next, I'll do 6. A to the, well, I did 4, 3. The next one is 2. 2 to the 0, 1. Well, the next one is 2. Plus 4. So we had a 1, a 4, a 6. The next one is 4. And now let's do a to the power 4, 3, 2. So the next power has got to be 1. Next, 2 to the 0, 1, 2. So the next one has got to be 3. Okay, 1 second. Plus. And now let's do the last coefficient is 1. A to the power 4, 3, 2, 1, 0. B to the 0, 1, 2, 3, 4. And I am done. And let's, how do you know this one is the tool to use? Okay, so again, n here is 4. The exponent of the binomial is 4. Therefore, you go to the row corresponding to 4. And so let's look at the row corresponding to 4. So 0, 1, 2, 3, 4. So this is the row I use. Now also note the following. The row can be found by, if the n is 1, Well, it's this one because that's a 1 there. If n is 2, well, that's a 2 there. The second number is 2. The second number is 3, so that's when n is 3. The second number is 4, that's when n is 4. And so it is this row because 4 is this second number. So notice this number is 4, this number is 4. Therefore, that is the row I should do. If you for Pascal's triangle, you would only use Pascal's triangle if this exponent was very small. You would never use Pascal's triangle for an exponent being large. You would use the binomial theorem. We're only going to be using Pascal's triangle for something that's very small. You would write out Pascal's triangle for a small exponent. And so in this case, when the exponent is 4. Yeah, probably. Yes, this will be recorded. This is being recorded. Okay, so so yes, uh, you would probably you wouldn't use it for anything. I mean, 6 is sort of I've never used past 6. 6 is really the upper limit. After that, well, actually, even that is really too high. I would use something else. I would use the binomial theorem for anything higher than 6, definitely. What page? Um, if you look in your book, okay, so if you look in your book, it tells you on page 675, 676, 677. Okay? So those are the pages that go over problems of this type to do the expansion using Pascal's triangle. Okay? So now let's finish this problem. Okay, so now let's finish this problem. And so 2 to the 0 is 1 times 1 is 1 times a to the fourth is a to the fourth plus 2 times 4 is 8, a cubed. 2 squared is 4 times 6 is 24, a squared. Plus 2 cubed is 8 times 4 is 32. 2 to the fourth is 16. And that is your answer. Let me do problem number 3. Okay, and so this is p minus q to the 5. Well, let's calculate this using Pascal's triangle. Yes, I will be going over all those in a few minutes. Let me do the first few examples first. Okay, so Pascal's triangle. So we didn't write Pascal's triangle up to 5, but I have it up to 4, so I can extend Pascal's triangle. So let's do a 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And let me drop down the 1. And so that's the next row in Pascal's triangle. Okay? So now let's write out the binomial expansion using these numbers in Pascal's triangle as the coefficient for this binomial expansion. And so this will be a 1 because there's a 1 here, p to the 5th, negative q to the 0, plus 5, because there's a 5 there, p to the 4th, negative q to the 1st, plus 10, because there's a 10 here, p to the 3rd, negative q to the 2nd, plus 5, p to the 2nd, negative q to the 3rd, plus, how did I go wrong there? There's a 10 there. There's two 10s. Plus 5, p to the 1, negative q to the 4th, plus 1, p to the 0, negative q to the 5. So now notice the following. The coefficients are 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. The numbers start with 5. So the exponent is 5. So 5, 4, 3, 2, 1, 0. And for q, it's the exact opposite. 0, 1, 2, 3, 4, 5. So I will show you that in about 5 minutes. That will be, once I get through these first few problems, okay, to do it without using Pascal's triangle, without doing this. Okay, so now q to the 0 is 1 times p to the 5th. Q to the 1st is a negative 1, so this will be a negative 5, p to the 4th, q. Q squared will be a plus 10, p cubed, q squared. Q to the 3rd will be a negative q to the 3rd is a negative q cubed, negative 10, p squared, q to the 3rd. A negative q to the 4th is positive, and so it's a plus 5p q to the 4th. A negative q to the 5th is negative, so it's a minus p to the 0 is 1 q to the 5th. Okay, so again, you wouldn't go out that far. You wouldn't go out to like, the 13th row or whatever. That's we will be using the binomial theorem to do that. Okay, and so I'll be using the binomial theorem. Okay, so once we have Pascal's triangle, these numbers give you the coefficients 1, 5, 10, 10, 1, 5 for the binomial expansion. And you just plug in and you get this value. Let's do 5. Let me do problem 5. It is x over 4 plus 2y to the 4th. Okay, so yes, so we're looking at Pascal's triangle. So recall, we actually had Pascal's, the 4th row in Pascal's triangle. As 1, 4, 6, 4, 1. So that was again the 4th row in Pascal's triangle. Well, the row corresponding to n equal 4 in Pascal's triangle, which is actually the 5th row technically in Pascal's triangle. Okay, bye. And so, let us do this expansion. So, I have a 1. I have x over 4 to the power 4, because that's a 4. And I start out with 0. Next, I have a 4. I already did 4, so I'll do 1 less, 3. And I'll up the 0 to 1 for the y part. Plus 6 is the next one. I have x over 4 to the power 4, 3, 2. For the y, I have 2y to the 0, 1, 2, plus 4, x over 4 to the power 4, 3, 2, 1, 2y to the power 0, 1, 2, 3, plus lastly, I have a 1, x over 4 to the 4, 3, 2, 1, 0, and a 2y to the 0, 1, 2, 3, 4. Okay, so this is equal to, this is equal to, yes, the exponent tells you the row, right? Again, the exponent, notice the second number in Pascal's triangle is the same as that exponent. Okay? And we'll actually be proving that in 5 minutes or 10 minutes or so. Okay? Next, let's expand this. Where do the variables come from? I don't know what you mean by where the variables come from. I don't know what that means. Okay, so this is equal to 4 to, okay, how many terms are in this equation? How many terms? I can figure that out. So notice that, well, you can notice this. Aha. And we'll do that way, way above. There's always one more. So notice when n is 0, 1 term. N is 1, 2 terms. N is 2, 3 terms. N is 3, 1, 2, 3, 4 terms. N is 4, 1, 2, 3, 4, 5 terms. There's always one more term than the exponent. And so, I forgot what the problem was now. The problem, this is power 4. And so, since the exponent is 4, that means that there are 1, 2, 3, 4, 5 terms. The reason for that is because you start counting at 0. So 0, 1, 2, 3, 4. So notice since you start counting at 0, there's always one more term than the exponent. Remember that in all these cases, how do I integrate? How do you integrate in the equation? I don't know what that means. How do you integrate? I'm not sure what you're asking. Okay. Okay, so I have x to the 4th over 4 to the 4th is 256. 2y to the zeros, well, that's just going to be 1 plus, and maybe I'll write this down, 4 times x cubed over 4 cubed, which is 64, times 2y, plus, and things are going to cancel, plus 6 times x squared over 4 squared is 16, 2 squared is 4, y squared, plus 4 x over 4 to the first is just x over 4. 2 cubed is 8, y cubed, plus x over 4 to the 0 is just a 1, plus 2 to, times 2 to the fourth, 16 y to the fourth. And so, let's simplify this. This is equal to yes, there's always one more term than the exponent. So if you have an exponent of 4, there are 5 terms. Okay, so x to the fourth over 256 plus, well, 64 divided by 8 is 8. So plus x cubed y over 8 plus 16 divided by 4 is 4. 6 divided by 2 is 3. 4 divided by 2 is 2. So 3 x squared y squared over 2 plus, 1 second, plus the 4's cancel. The 4's cancel. So you get 8 x y cubed plus 1 times 16y to the fourth is 16y to the fourth. And that is your answer. I need tools. Okay. No, you're not allowed a cheat sheet on an exam. Okay, so this is the binomial expansion for that particular expansion. Let's recall again how you write the binomial, how you write Pascal's triangle. You always start with 1, and then to find the next number, you add what's above. 1 plus 1 is 2. You bring down the 1. Next, you drop down the 1. 1 plus 2 is 3. 2 plus 1 is 3. Drop down the 1. Drop down the 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Drop down the 1. To get to the next term, I guess I did over here in Pascal's triangle, you drop down the 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Drop down the 1. So you can keep doing this expansion, but again, you wouldn't go very far because this, it takes up a lot of room. That's why we will be doing these using the binomial theorem. How do you remember the variables? Oh, easy. This is the number 4. So you start 4, 3, 2, 1, 0. And for the other one, you go 0, 1, 2, 3, 4. That's always the pattern. Okay? Notice you have 5. So you go 5, 4, 3, 2, 1, 0. And the other one, you go 0, 1, 2, 3, 4, 5. That's always the pattern. Okay? Let's look at this guy. This is a 4. So you do 4, 3, 2, 1, 0. And for the other one, you go 0, 1, 2, 3, 4. That is always the pattern. Okay? Let's do the next one. Problem number 7. So notice it's always the same pattern. So A, B, minus y over 3 to the 5th. Okay, so let's do that. And so, it's this one. And so we've actually already done that. So 1, 5, 5, 1, 5, 10, 10, 5. So let's look at Pascal's triangle. So we've already done that. It was 1, 5, 10, 10, 5, 1. There should be 6, 2, 4, 6 numbers. Yes. Okay, so this should equal. There's a 1 here, so I'll put a 1. Next, this is the number 5, so I'll put an exponent of 5 here. Y over 3. You always start at 0 for the second term. Again, and next, I have a 5, a number 5 here, so that's my coefficient. Next, I started with 5, so I'll go down to 4. And I have a negative y over 3. I started with 0, so the next term is 1. Next, I have the coefficient 10. I have AB to the 5, 4, so the next term is 3. For the negative y over 3, I have 0, 1, 2, plus the next term is 10. So I have a 10 here. And then I have AB to the 5, 4, 3, 2 is the next term. Negative y over 3 to the 0, 1, 2, 3 plus 5. That's the next coefficient. AB to the 5, 4, 3, 2, 1. Negative y over 3 to the 0, 1, 2, 3, 4 plus, lastly, 1 AB to the 5, 4, 3, 2, 1, 0, negative y over 3 to the 0, 1, 2, 3, 4, 5. And then let's simplify this. Are you just plugging in? So I am these numbers here in Pascal's triangle are the coefficients in front of the binomial expansion. Then the exponents on the terms in the binomial expansion, you start out with this exponent, and then you go down 5, 4, 3, 2, 1, 0. For the other one, you start at 0 and you go up to 5. 0, 1, 2, 3, 4, 5. And that is your binomial expansion. That is the pattern that you should follow. And so this is equal to, yes, remember, since the exponent is 5, there's always one more term. There's one more terms. So there are 6 terms in this expansion. 1, 2, 3, 4, 5, 6. Okay? Okay, so this is equal to a to the 5th, b to the 5th, just raising both a and b to the 5th power. Oh, and maybe I'll have to actually, so this is times 1. Negative y over 3 to the power 0 is again 1. Okay. Plus a negative y over 3 to the first is going to be a negative number. 5 times a to the 4th, b to the 4th. Y over 3 to the first is just y over 3. Plus 10 a cube b cube raising each of the factors by the product in that. And so negative y squared is just y squared. 3 squared is 9 minus 10. AB quantity squared is just a squared b squared. A negative y cubed is negative y cubed. 3 cubed is 27 plus 5. A to the first, b to the first is just ab. Minus y to the fourth is y to the fourth. Over 3 cubed is 81. Minus 1 times, well, ab to the 0 is just 1. Negative y to the fifth is a negative y to the fifth. 3 to the fifth is 243. And so this is equal to we're expanding, we are simplifying. So we're simplifying. It's the same as if I had said multiply this out 5 times together. What number do you get? It is, however, we're using a simplifying concept, and the simplifying concept is to use Pascal's triangle to figure out what this product is, rather than actually having to multiply it all out 5 times. And so it's an easier way of simplifying. Yes, it is. It's simplification. It's an expansion. Okay. And so 1 times a to the fifth, b to the fifth times 1 is just a to the fifth, b to the fifth. Minus, well, this will be 5/3 a to the fourth, b to the fourth, y. What is the risk? Okay, so again, use Pascal's triangle. Yes, so what we're doing is we are simplifying. And so 10 divided by 9 times a cubed, b cubed, y squared, minus 10 over 27, a squared, b squared, y cubed, minus, I guess I'm going to have to move this over a little bit so I can get it all in one space, one line, minus 5 over 81, AB y to the fourth, that's a plus, minus y to the fifth over 243. And that is your answer. So yes, this is the answer. So you just simplify the last little part. Let me do problem 9. Okay, so for problem number 9, it says in exercises 9 through 12, use the binomial theorem to write the first 4 terms of the binomial. Okay, so the binomial theorem says this is equal to 2x plus 3y to the 10 is equal to the sum, and maybe of r equaling 0 to 10 of NCR 2x to to the n minus r, 3y to the r. So in this case, I'm going to only use the binomial theorem to expand this. Well, you try to multiply. So do this, do AB minus y over 3 that's 1, 2, 3, 4. Multiply that out. And so if you multiply that out, you're going to get a long answer. So that's what the answer is. So actually multiply all that out and you'll see that you get the answer that I wrote above. And so yes, it's long because, well, we've asked you to do a big expansion. Okay. So do it and see if you ever get the correct answer. Do this to the 10th power and see if you can do it without making an error in doing 10 multiplications. Yeah. Okay, so this is equal to. Okay, so let's do this. And so by the binomial expansion, this is 10c0 2x. So now I'm going to just do 2x. What is 10 minus 0? 10. 3y to the, now I just put the 0 here. So this will be the following recipe that we'll use. We look here at this exponent, and I put the exponent here on top. Then I start with 0. And then I'll do 1, 2, 3, all the way up to 10. I do 10 minus 0, and that will be the exponent for this guy. And then this number here at the bottom will be the exponent for that guy. And then I add them all up. This is page 675. I don't know what that is. What is on page 675? Page 675. Oh, yeah, so that's what we were doing above. So we were doing that for these first few problems. And so we were using Pascal's triangle to expand these binomials. And so that's what I was doing. Okay, so let me write out the binomial expansion, and then we'll do the calculation. And so next, 10c1, 2x to the power. This is 10 minus 1 is 9. 3y to the power. I have here a 1, so I'll put a 1. Plus 10c2, 2x to the 10 minus 2 is 8. 3y to the 2, because that exponent is 2, plus 10c3, 2x to the 10 minus 3 is 7, 3y to the 3, plus 10c4, 2x to the 10 minus 4 is 6, 3y to the 4, plus 10c5, 2x to the 10 minus 5 is 5, 3y to the 5, plus, let me write out the last part of the expansion, 10c6, 2x to the 10 minus 6 is 4, 3y to the 6, plus 10c7, 2x to the 10 minus 7 is 3, 3y to the 7, plus 10c8, 2x to the 10 minus 8 is 2, 3y to the 8, plus 10c9, 2x to the 10 minus 9 is 1. 38y to the 9 plus 10c10. 2x to the 10 minus 10 is 0. 3y to the 10. This is the binomial theorem, yes. This is the binomial theorem that we're using. So notice the following pattern. So we're just plugging into this formula, okay? So notice the following pattern. The binomial coefficients always has this exponent of 10 at the top. So this is always, the n is always at the top. Next, the bottom goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So it goes from 0 to the exponent. Next, these exponents here are found by just, for the first, you just subtract. 10 minus 0, 10. And then you put the 0, same exponent. 10 minus 1, 9. The 1 is put here. 10 minus 2, 8. You put the 2 here. 10 minus 3, 7. You put the 3 here. 10 minus 4, 6. You put the 4 here. 10 minus 5, 5. You put the 5 here. 10 minus 6, 4. You put the 6 here. 10 minus 7, 3. You put the 7 here. 10 minus 8, 2. You put the 8 here. 10 minus 9, 1. You put the 9 here. 10 minus 10, 0. You put the 10 here. Okay? And that is your binomial. Does it show it up to 10? I don't know. I have to look. Does it show up to 10? What page was that? It shows it up to 4. So I do up to 4. Okay? On the book. Look. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the pattern. The numbers here go from 0 to 10. Okay? Next. Sorry. Okay. 1 second. Okay, wait 1 second. Going back and forth. I lost the book now. Okay, so sorry about that. Oh, it's back. Okay. 1 second now. See if I can get this back. Darn. Why is it not working? Okay. 1 second. Okay, sorry. I can no longer see. Okay, wait 1 second. Sorry, going back and forth. Kill the. Yeah. Okay, sure. It's just that going back and forth just killed my book. That's all. Wait 1 second. Just wait 1 second, okay? And let me get to it again. Okay. Okay, I can see the book again. Okay, sorry about that. It's just going back and forth just killed me a little bit. Okay. Okay, so good. So now I'm back. So this is equal to. Calculate 10C0. That's a 1. Again, just do it on your calculator. 2 to the 10th, 1024. X to the 10. 3y to the 0 is 1, plus 10c1 is what, 10? 2 to the ninth is what, 512, x to the ninth times 3y plus, you're plugging in first equation binomial tree. There is no binomial tree. First equation to binomial, okay. Just plug into your calculator, 10c0, okay? And so if you do that, or I just sort of calculated in my head, just figure out what that is. Are we using scientific? Numbers are not that big. 1 is not a big number. 1,024 is not that big of a number. No number is really that big. Okay, and so 10c2, why not? Why scientific not? I don't know why. Why? These are not very big numbers. 10 is not a, you don't need to use scientific notation for the number 10. Why use scientific notation? Well, you don't need to. These aren't you would only use scientific notation if you were dealing with large numbers. This is not a large number. So this is going to be what, 45? If I calculate this correctly. People should be checking this on their calculator. And this is what, 256 x to the 8 times 9y squared. Actually, I should probably start calculating these on my calculator. And then 10c3. Oh, and they actually, okay. And so that's, let me actually do that on a calculator. 10c3. Oh, yeah, well, that's good. And so 10c3 is 120. What am I doing? 2 to the 7th. So I decided to actually 128 x to the 7. 3 cubed, 27 y cubed. What are the fewest button to compute is massive string number string? Depends on if you're talking about a particular calculator. It depends on your calculator how you would calculate NCR. It's located somewhere on your calculator. Usually the least number of buttons you have to hit is 3 buttons. You know, or in this case, well, 10, you have to have, you know, the 2 digits for the 10. But, you know, so it's just, you plug in 10, hit the NCR button, and then the number, whatever, you know, you want to compute 3. And that would give it to you. So it depends on what number you're calculating. Okay. So, okay. Look again. Okay, let me finish this calculation. But again, all exams, if you just look at the final exam, there's a sample, and the problems on the final exam are identical to the problems on the sample final. So if you want to figure out what type of problems are on the final, you look at the sample final just like you did for all other exams in the course. Okay, so okay, yes. Okay, so I'm sorry, where am I now? 0, 1, 2, 3, 4. So I'm doing 10C4. So 10C4 is 210. 2 times 2 to the 6, 64. x to the 6th, um, uh, 3 to the 4th, 81, y to the 4th, plus 10c5, which is 252, 10c5, 2 to the 5th, 32, x to the 5th, times 3 to the 5th, 243, y to the 5th, plus 10c6, which is 210, 2 to the 2 to the 4th, 16, x to the 4th, 3 to the 6th, 729, y to the 6th. No, I'm not using a reference. There is no reference chart. Okay, so I'm looking up. What I'm doing is I'm looking here. I'm looking at these numbers. Okay, so I'm just looking at these numbers here. Okay, plus 120. 2 cubed is 8x cubed, plus 2 to the 3 to the 7th, which is 2187, y to the 7th, plus 10c8, which is 45, times 4 x squared, times, oh, why do I put a plus there? Oh my goodness. Times, sorry about that, times 65, 61, y to the 8, plus 10, 2x, times, that's 19,683, y to the 9, plus 1, 2x to the 0 is 1, times 59,049, y to the 10th is equal to. Okay, so let's just multiply those numbers out. 1,024 x to the 10 plus 512 times 30, which is 15,360 x to the 9 y, plus 45 times 256 times 9, which is 103,680 x to the 8 y to the 2nd. Of course, you would not write, all you need do is write this. This is all, the binomial theorem right there. That gives you all of them. You don't have to write them all out because you have very handy in that expression all of these. Okay, so x to the 8th. So plus 120 times 128 times 27. And so plus 414,720 x to the 7, y to the 3, plus, yes, I'm just plugging into that formula. That's all I am doing. Plus 6, plus, 210 times 64 times 81 is 1,088,640. X to the 6th, y to the 4th. I'm just small things, huge things. Okay. Plus 252 times 32 times 243 is 1,959,552. Just multiplying 252 times 32 times 243, x to the 5th, y to the 5th, plus, they're always, so if this is 10, remember, if the exponent is 10, that means there are 11 terms. 1, 2, 3, 4, 5, 6. I've done my 6th term. Now let's do the 7th term. Plus, so I'm going to do 210 times 16 times the 729. And so 2,449,440 x to the 4, y to the 6, plus 120 times 8 times 2187 is 2,099,520 x cubed y to the 7 plus 45 times 4 times 6561 is 1,180,980 x squared y to the 8th plus, only 2 more terms left, plus 10 times 2 times 19,683 is 393,660 x y to the 9th plus the last term. Each part of the process is easy. One time like this, 1 times 59,0949 is 59,049 y to the 10th. If you do the calculation as I'm doing it, it's each step is small. And that is your expansion. Okay. Let me do problem number 11. Oh, it is 2x minus y over 3 to the power 7. Okay. So actually, uh, I while I was doing it, there were so many questions asked. I forgot that I only need to write the first 4 terms. That's why it looks so long, because I only needed 4 terms. Okay, that's okay. So, so the actual problem actually only asks for the first 4 terms. So let me do this. So let me actually only write out the first 4 terms for this. That's why it's then it won't be look as nearly as long. So this should equal 7c0, 2x to the 7 minus 0 is 7, negative y over 3 to the 0, plus 7c1, 2x to the 7 minus 1 is 6, negative y over 3 to the first, plus 7c2, 2x to the 7 minus 2 is 5, negative y over 3 to the, again, the number here is 2. What is the question? So the question is, in exercises 9 through 12, use the binomial theorem to write out the first 4 terms in the expansion of the binomial. So I'm writing out the first 4 terms in this expansion. So I'm going to just write out these first 4 terms, okay, rather than the whole expansion. So I'm only going to write out these 4 terms, okay. So if I multiply this guy 7 times, then write out the first 4 terms when you will have written this and as a in descending order. So if you write this expansion in descending order, just give me the first 4 terms. What is 7? Never 0. I don't know. I don't know what 7 never 0 is. What is 7? Oh, remember this notation. That is the binomial coefficient 7c0. We will calculate. It'll equal 1. So 7c0 is 1. Plug that into your calculator, and you'll see that 7c0 is just the number 1. Right. So remember, we did these. Remember back here. We did this at the very beginning of class. Here's the binomial coefficient. So the binomial coefficient NCR is n factorial over r factorial times n minus r factorial. We could compute it by just writing out the first few terms over the factorial. So if I want to compute, remember the 12C4, I would write out the first 4 terms over 4 factorial. Or I could look in Pascal's triangle and find the coefficient. Okay? So that was the binomial coefficient. Okay, so it only says to write out the first 4 terms. So 1, 2, 3, 4. So notice I start out with, I have a 7 here, and then the bottoms is 0, 1, 2, and 3. To figure out these exponents, I do 7 minus 0, 7 minus 1, 6, 7 minus 2, 5, 7 minus 3, 4. And then these give me my other exponent, 0, 1, 2, 3. I know, but has a complex fraction to a power. Yeah, but that's not a complex fraction, really. Uh, you know, 3 to the first is 3, 3 squared is 9, and 3 cubed is 27. So they're not really big numbers. Okay, so let's do this. So 7c0 is 1. 2 to the 7th is 128. Negative y over 3 to the 0 is 1. Seven C1 is 7. 2 to the 6 is 64. X to the 6. Negative y over 3 to the first is a negative y over 3. So that's why this plus sign becomes a minus. 7C2 is 21. 2 to the 5th is 128. Negative y squared is y squared. 3 squared is 9. Okay, so minus 7C3. And so 7C3 is just 35. 2 to the 4th is 16. No, it's not. It's 64. 64. X to the 4th. A negative y cubed is a negative y cubed. And 3 cubed is 27. Plus etc. And so let's just simplify this. These are really okay. So you can either write it vertically or horizontally. Doesn't really matter. So this is equal to 1 times 128 times x to the 7th. The divide pattern. I'm not sure what a divide pattern means. 1 times 128 times 1 is 128. X to the 7 minus 7 times 64, 448 over 3, x to the 6, y plus, okay, one question. If you could, okay, but I'm not sure in this case. I do use colors, but I'm not sure in this case where to use colors. Okay, plus 21 times 128, 2688 over 9, x to the 5th, y squared, minus, oh, actually, minus 35 times 64, 2240 over 27, x to the 4th, y cubed, plus a whole bunch of other terms. They only wanted the first 1, 2, 3, 4 terms. And so that's the first 4 terms in this expansion. And so since they only wanted 4 terms, it's obviously going to be smaller. It's going where? Place everything. Are you multiplying? Yes, I am multiplying. 1 times 128 is 128. 7 times 64 is 448. 21 times 128 is 2688. 35 times 64 is 2240. Okay, let's do problem number 13. Okay, so let's do problem number 13, which is 3x minus y to the 8th power, Find the third term. In exercises 13 through 21, find the indicated term in the binomial expansion. So in this case, I want to find the third term. So notice that each term in the binomial expansion just looks like NCR x to the, n minus r power y to the r. So all I have to do is figure out, well, what r is. Well, let's look here. So I want to do the third term. So notice here it is. The first, second, third term, notice the r here is 2. The first, second, third term, this number down here is 2. And so to find the third term, all I have to do is, well, this number here is 2. This number on top is always this exponent. Next, to find this exponent here, subtract 8 minus 2 is 6. To find this exponent, you just use this number 2. The infinity formula. Either formula, in this case, either formula works. You can use the one that doesn't have the infinity in it. They both give you the same answer. Okay. And so let's calculate each of these. And so let's calculate, okay, 1 second. No. Okay, so, and so let's calculate 8C2. 8C2 is 28. 3 to the power 6 is 729. X is 6. Negative y squared is just y squared. And so let's multiply 28 times 729. And so I get 20,412 x to the 6, y to the second. And that would be the third term in your expansion. And so in this case, we only want to find one term. And so the calculation is going to be much smaller. Sure. Okay. So again, I want to find the third term. And so to find the third term, since I started counting at 0, that means I want, and so first off, I have an exponent of 8. So in the binomial coefficient, this number on top will be 8. Next, I want the third term. Well, since I start counting at 0, I want 1 less than 3, 2. Now, I have here a 3x. To find the exponent, I just subtract. 8 minus 2 is 6. Next, I have a negative y. To find the exponent, I just use this number 2. And then you just calculate 8C2. 56 divided by 2 is 28. 3 to the 6 is 729. A negative 1 squared is positive. And then you just multiply the 28 times 729, 20,412. And that's your answer. So your answer is 20,412 x to the 6, y to the second. Let me do problem 15. And so problem 15, x squared plus 2 to the 11th, and I want to find the 10th term. So let's do this. So we're almost done with this lecture. Um, there'll still be a few more things to do in this lecture. Okay, so let's find the 10th term. So again, the exponent is 11, so the number on top will be 11. Now, since I want to find the 10th term, then the number on the bottom will be 10 minus 1, 9. Okay, next, I want to find the exponent of the x squared. The exponent of x squared will just be 11 minus 9, 2. Next, I want to find the exponent of 2. The exponent of 2 will be 9. And so, uh, 11 times 5 is 55. So 10c9 is 55. X squared squared is x to the 4th. 2 to the power 9 is 512. And so let's multiply this out. And so you get 28,160 x to the 4. And that is your 10th term in this expansion. What is the 9? Okay, so remember, 10 minus 1 is 9. So just like above, 3 minus 1 is 2. And so I will take, since I start counting at 0, I'll take 8c2. Since I start counting at 0, the 10th term would be the 11c9. Okay? That will be the binomial coefficient for the 10th term. Let me do problem number 17. And so I have here a squared minus 2b cubed to the power 10. Now it asks you, what is the middle term? Okay. So let's look up at Pascal's triangle to figure out what they're saying. Oh, okay. So notice that if I exponent of 0, the middle term is the first term. If I have exponent of 2, then the middle term is this second term. If I exponent of 4, the middle term is the third term. Okay, so if you take the number 4, divide it by 2, you get 2. You add 1 to it, it'll be the third term. Or actually, even better, notice that r in this case is 2. And so if you have 0 divided by 2, the first term, which is the corresponding r equals 0, is the middle term. If I have 2, then I divide by 2, that gives me 1. So r equaling 1 gives me the middle term. If I have 4, 4 divided by 2 is 2, and that will give me the r for the middle term. So to figure out the r for the middle term, all I need do is divide 10 divided by 2 is 5. And that will give me my r. Okay. Yes. So, okay. So in this case, the middle term is when r is 5. And so the exponent is 10. So that will be the number on top. The number on bottom is 5. Let's figure out the exponent of a squared. 10 minus 5 is 5. Let's determine the exponent of the negative p cubed. Well, this number here is 5. And so let's calculate 10. Okay, 1 second. C5. What does the middle term mean? The guy in the middle. 3, 7, 8, 9, 11. What's the middle term? What's 8? Okay, it's the guy in the middle. That's what the middle term means. Yes, that's the middle. Okay, and so in this case, let's look up. We actually did some expansions. Here's 10. So here I could say, what's the middle term? Well, notice there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms. Therefore, the middle term is 1, 2, 3, 4, 5. This term here, this guy is the middle term because there are 1, 2, 3, 4, 5 terms before it, 1, 2, 3, 4, 5 terms after it. So this is the middle term. Okay. Let's look here at this term, 4. There are 1, 2, 3, 4, 5 terms. So the middle term here is this third term because there are 1, 2 terms before, 1, 2 terms after. Notice 4 divided by 2 is 2. This corresponds to, oh, I didn't have that expansion. It corresponds to that 6. It corresponds, so notice 10 divided by 2 is 5. So this middle term here, the 10C5, this term here, corresponds to the middle term. Okay, so let's calculate this. What about problem 17? Yes, let's calculate this. So 10C5, so 10C5 is 252. 2 times 5 is 10. Negative 2 to the 5th is is negative 32. B to cube to the 5th is b the 15th. And so let me multiply this out. So 252 times 32, negative 32, is a negative 8,064. A to the 10, b to the 15. And that is your middle term. How? What is a to the 10th? Yes, it is a to the 10th. Correct. Okay, so let's do problem number 19. Then what is, I'm multiplying. 252 times a positive 252 times a negative 32, we're multiplying, remember, is a negative 8,064. Okay. Let me do problem number 19 and the exponent. 2 times 5 is 10. 3 times 5 is 15. And those are the exponents. Okay. So now let's do 2x squared plus 1 over x squared to the 6th power. I want to find the constant term. Meaning a number a term that doesn't have any powers of x, or of any variable. It only has numbers in it. So I want to find somehow, if I do an expansion, of course none of these, oh wait, I think maybe the first one did. No, maybe not. I want to find some term that doesn't have any variable in it. So I don't know where that's going to lie. So I'm going to have to figure out that first by use the binomial expansion. Okay? And so the question is, find the constant term in the expansion. So if I write out this huge expansion, um, when will I get a constant term? Well, notice that for every term in the expansion, it has this form. Well, and maybe I'll put an actual, the exponent is 6. Okay? And then I have a 2x squared to the power 6 minus r. And then I have a 1 over x squared to the power r. All of them look like this. And somehow I want that this is equal to some constant, meaning that the x term is 0. So somehow I want to figure out r so that x, the exponent of x, is 0. So let's find r. That's the first thing to do. Well, I don't care about the constant yet. I just want to figure out r. So let me not write any constant. Let me not write the binomial coefficient 2 to some power. Let me only write the x's. So I'll only write down the x's so that I want x to the power 0. Well, we'll figure that out if the constant term is 2. Okay, so let's figure that out. So if you do this expansion, what is the constant term? Well, let's check. Okay, so x squared to the power 6 minus r is just x to the 12 minus 2r. X to the 1 over x squared to the r is x to the negative 2r. These are r's. I want that to equal x to the 0. Well, I have the same base. I'm multiplying, so add exponents. So this is x to the power 12 minus 4r. I want that to be x to the 0. Since the exponential function r is the, it's what r is when you get, it's the r in the binomial coefficient that gives you the constant term. It is r plus 1 is that term. So it's the r plus first term. If the r plus first term is the constant term, then that's r. Okay. Again, it's better just to think of it as r in the binomial coefficient. So since the exponential function is injective, since these quantities are the same, and since the base x is the same, then the exponent must be the same. Add 4r to both sides of your equation. And so 12 is equal to 4r. Divide both sides of your equation by 4. So r is equal to 3. And so the fourth term is the middle term. Okay? And so now I can find the constant term. So the constant term we always use normal math. And so, uh, and so, Every step is easy. And so now let's figure out what this is equal to. So the constant term will be 6 C3 times, yes, I'm plugging in R. So that's all I'm doing is plugging in R into here, times 2x squared to the power 6 minus 3, 3, times 1 over x squared to the power 3. And so this is equal to, wow, and so I'm all tied up in something. Okay, so this is equal to 22 cubed is 8 x to the 6 times 1 over x to the 6. Okay, yes, please just need to see. Kicks and punches. Okay. Um, okay, so 20 times 8 is 160. The x to the 6's cancel. So the constant term is the number 160. So notice that in this expansion, all of a sudden you just get a number. And that's what we want to figure out. What is that number? 160. Let me do problem number 21. It's a nice small number, so it should be, what is, so, right. So if you do this expansion, right, and so in the expansion you'll have a whole bunch of terms. Okay. And so if you look at, these terms, it'll be something like 64 x to the, what is that, 12 plus, so a whole bunch of terms. Well, one of them is going to be, the middle term is 160. And so that middle, so they have 7 terms. So 3 terms before it will be something, 3 terms after it will be something, but this term in the middle is 160. I'm sorry, the exponent is 6, isn't it? The exponent is 6. Therefore, there's 7 terms. Remember, the number of terms is always 1 more than the exponent. Remember that? Yes. Okay. And so there are 7 terms in this expansion. 3, uh, there are 3 to the right, 3 to the left. And so the middle term is 160. Okay. Okay. So that was 19, I think, right? So problem 19. Let me do. Okay, so that was problem 19. So let me do problem 21. X to the 4th minus 3x squared to the 4th. To the 6th, I'm sorry, to the power 6. I want to find the constant term. Okay. And I want to figure out what is that constant term. So again, I want to find R. Okay. So this is just going to be x to the 4th to the 6 minus R, 1 over x squared to the R. I want that to be x to the 0. Just like before, I'm not writing down any of the constants in the binomial expansion in a particular term in the binomial expansion. I'm just writing the variables with their exponents so that I can figure out what exponent will give me and what term will give me exponents that all cancel out to be just an exponent of 0, like what we did. Sure. So, just like in the previous problem, each term in the binomial expansion will be some constants involving x's to powers, and we want that these x's to these powers to be x to the 0. And so just writing down the x's without any of the constants, let's determine r. And so I'm just going to determine what r is, so that in the binomial expansion, that term happens to have it happens to have x to the power 0 in that term, so that it's a constant term. Yes. So you want to find r. It's the same step. 1. So step 1 is to find r. X to the 0 is 1, correct. And so so that means that you're going to have a constant term. So I have x to the 4 times 6 minus r is 24 minus 4r. 1 over x squared to the r is x to the negative 2r. Since I have the same base, add exponents. So I have x to the 24 minus 6r. I want that to equal x to the 0. Since the exponential function is injective, since these values are equal, since the bases are equal, then the exponents must be equal. And so I have that 24 minus 6r must equal 0. Let's solve for r. I keep getting tied up, sorry. My tablet has this string attached to it. So sorry about that. Okay, so plus 6r. And so 24 is equal to 6r. Divide both sides of my equation by 6. So r is equal to 4. Yes. So r is 4. And so now let's figure out what the constant term is. And so the exponent is 6. R is 4. The first term is x to the 4th. 6 minus 4 is 2. The next term is a negative 3 over x squared. And the bottom term is 4. Okay, so let's do this. And so let's calculate 6c 4. So that's going to be 15. X to the 4th squared is x to the 8th. Negative 3 squared let's say 8 is a positive 81 over x to the 8th. 6c4. Where are you? Okay, so 6c4, same as 6c2, so 30 divided by 2 is 15. So calculate 6c4 on your calculator. 30 divided by 2 is 15, so that's 6c4. 2 times 4 is 8. A negative 3 to the 4th is equal to 81, positive 81. X squared to the 4th, 2 times 4 is 8. Notice that the x to the 8ths cancel. And so let me just multiply. 81 times 15, 1,215. And so the middle term is 1,215. So that's the middle term in my expansion. Okay. So let me give you some properties of Pascal's triangle? That will help you to compute some of these values. Ah, and that's what I'm doing. That's what I'm going to do right now. So I'll tell you how I'm doing that. So I'll give you the properties of Pascal's triangle. And so let me do, let's figure out how I calculated each of these so quickly. Uh, let n here be a whole number, I guess, for all of these. And so 1. Um, NC0, I want to show that that's always equal to 1. Okay? And so NC0, well, let's recall the definition of NCR. Recall that, and maybe I'll do that first. So let's just do one recollection. Actually, it's 1:30. Let's see, how long is this supposed to last for? Mr. or Mrs. Uh, Captioner? As long as it takes. No, no, no. I'm asking the captioner. The captioner. Do you remember? She may not remember. Or she or he. 2:15. Oh, so we have 20 minutes. Okay. So we can probably get it done in 20 minutes. Okay. We'll do that. So let's just recall. Okay, um so let's just recall here the following, that NCR is equal to n factorial over r factorial n minus r factorial. Therefore, NC0 is n factorial over 0 factorial n minus 0 factorial. Just by the definition, this is the definition of the binomial coefficient. So that was the definition that we gave earlier. And so n minus 0 is just n. The n factorials cancel. 0 factorial is just 1. So this is equal to 1. And that's what you wanted to show. Oops. Okay, so let me do the second one. NC1 is equal to n. So notice that what did it tell us about Pascal's triangle? This told us that in Pascal's triangle, the leftmost numbers are always 1. These are properties of Pascal's triangle. So I'm showing you some properties of Pascal's triangle. So if I'm looking up here, if you look at the triangle, Pascal's triangle, maybe I'll just sort of quickly recall, just do the first few. So the first thing that I showed here is all these numbers are 1. That's what was problem 1. So now let's do problem 2, which says, well, let's see, NC1 by definition, just using this definition here, is n factorial over 1 factorial times n minus 1 factorial. But by definition of factorial, Recall that n factorial was defined as n times n minus 1 factorial. Then this n factorial is n times n minus 1 factorial over 1 factorial times n minus 1 factorial. Well, the n minus 1 factorials cancel. 1 factorial is 1. N divided by 1 is indeed n. So I'm done. So this second one says that, well, all of these numbers here, the second numbers, are always the same as this first number on top. It's always the exponent. So notice it was always that exponent in the binomial expansion. Okay? Let me do the third one, third property here. NCR is equal to n over c n minus r, which is actually one that I've been using a lot. So notice that this Pascal's triangle is symmetric, that one half looks like the other half. And so notice that if you look in half of here, split in half, then one half looks like the other half. Okay? And that's what this is saying. Okay. Well, let's show this. N C n minus r is equal to, by definition, so let's just use this definition here. This is equal to n factorial over n minus r factorial times n minus r factorial. Okay. Now, I have a minus outside the parentheses. Let's change all the signs inside the parentheses. So this is n minus r factorial, and then this is n minus n plus r factorial. Just changing all the signs inside the parentheses. We are proving this. So that NCR is equal to NC n minus r. Now notice that the n's cancel. So this is equal to n factorial over n minus r factorial times r factorial. Well, multiplication is commutative, so I can write this as r factorial, n minus r factorial, but that is just NCR. And that is what I wanted to prove. Next. If I look at NCR minus 1 plus NCR, that's equal to n plus 1 CR. And so this is, right, these, okay, so these are properties of Pascal's triangle. These will help you in computing. So notice, say problem number, so notice this symmetry here says the following. How did I compute 6C4? I noticed that that's the same as 6C2. So I just did 6C2, which is 6 times 5, 30, over 2 times 1, 2. 30 divided by 2 is 15. So that aided me in all of these calculations. So these properties of Pascal's triangle are aids to computations. Okay. Now notice the following. This says in Pascal's triangle to find the value of something below, you just add the ones above. So 3 is 1 plus 2. Okay. And so that's how you compute the numbers in Pascal's triangle. So far. Okay, so this is the fourth one. So let's prove this. So I have n CR minus 1 plus NCR is equal to n factorial over R minus 1 factorial n minus R minus 1 factorial plus n factorial over R factorial n minus R factorial. So this is equal to n factorial over R minus 1 factorial. I can write this as, again, changing all the signs inside the parentheses. This is just n minus R plus 1. Okay. And this is n factorial over R factorial n minus R factorial. This is these are proofs that the formulas work. Okay. So this is a computational proof. Okay, so, oh darn. 1 second. And tell me if the screen goes blank when I do this. Hopefully not. Can you still see me? Blank. Okay, 1 second. Now you should be able to see it. Okay, so let's get a common denominator. And so the common denominator is, well, let's multiply and divide by R. Let's, wonder why. Let's multiply. Let's multiply and divide by n plus 1 minus R. And so you notice here that R times R minus 1 factorial is R factorial. N minus 1 factorial times n plus 1 minus R is n plus 1 minus R factorial. And so I get the common denominator of R factorial over n plus 1 minus R factorial. And I get these two terms that I'm adding. N factorial R plus, let me multiply the n factorial inside the parentheses. Let me write this as n plus 1 minus R. Notice that the n factorial r's cancel, and n plus 1 times n factorial is n plus 1 factorial. And let's write this as n plus 1 minus R. in parentheses. So let me write this as, well, this is just n plus 1 CR by the definition of the binomial coefficient. And so I am done. Yes, all I'm doing, I found the common denominator, and then I added the two fractions. Let me do number 5. It says that the way that you find the number in Pascal's triangle is you add the two above. Okay, that's what it says. Okay, next I have that the sum of NCR is just equal to 2 to the n. So if I add up all these binomial coefficients, I just get 2 to the n. So let's prove that. So first, let's recall the binomial expansion. And so I have the binomial expansion. And so let me just do that. Note that 1 plus 1 is 2. And then we're done. So long as you know that 1 plus 1 is 2, let's plug this into the binomial expansion. So this is r to the 0, r equals 0 to n of NCR. X is 1, y is 1, 1 to the any power is 1. So this is the sum, r equals 0 to n of NCR. And so I'm done. So notice what this says is that if you look at let me go all the way to the top then. So if you look here, well, 2 to the 0 is 1. 2 to the 1, 2 is 1 plus 1. 2 squared, 4 is 1 plus 2 plus 1. 2 cubed, 8 is 1 plus 3 plus 3 plus 1. 2 to the 4th, 16 is 1 plus 4 plus 6 plus 4 plus 1. So if you add up all the numbers in each, I accidentally put a little mark there, didn't I? Yes, I did. If you add up all the numbers in each row in Pascal's triangle, that's just going to be 2 to the power of, well, the second term in the of that particular row. Okay, let's do 6, contraction. R times n minus 1 r minus 1. In this case, actually, let me do it this way. R NCR is equal to n minus 1 r minus 1, where r here is an integer, and so r and n are natural numbers. Is this approved? Well, it will be eventually when I prove it, yes. So it's a formula. So let's prove this formula. Each of these are formulas that I'm giving you. It's properties of Pascal's triangle. This is called contraction. It's a very important property. You'll use this in statistics and many other places, but certainly in statistics, this will be important. Convergence. No, this has nothing to do with convergence. Okay, so let's show this. Okay. And so R times NCR. Well, again, NCR by definition is n factorial over R factorial n minus R factorial. Let me write n factorial is n times n minus 1 factorial, like what we did before. Let's write R factorial as R times R minus 1 factorial. Next, notice that the difference of any two terms is translation invariant on those two terms. So if I add 1 to n and 1 to r, I actually have the same difference, n minus r. Okay. Oh, actually, I probably want n minus 1, right? Let me do, suppose I subtract 1 from each of these. So if I subtract 1 from n and from r, their difference is still the same. Okay, so now the r's cancel. And so this is equal to, let me write the n first, n times n minus 1 factorial over r minus 1 factorial times n minus 1 minus r minus 1 factorial. But by definition of the binomial coefficient, this is just n minus 1 cr minus 1. And that is what you wanted to show. Okay, so I'm giving you these are differing properties of Pascal's triangle of the binomial coefficients that would be helpful in the future. As a matter of fact, this is also actually a very helpful one to compute values of, you know, that you happen to have in your, say, Pascal's, in your binomial expansion. When you do the binomial theorem, if you just would have multiplied by r over n, you would have gotten the next term in your, actually that's how you get to the next term. Because the definition of the binomial coefficient is in terms of factorials. That's the definition. That was the definition of that here is the definition of the binomial coefficient. Okay? And so what you should have noticed is how I computed those so fast. So I just did 7 over 1, 6 over 2. So if you go from, so to compute this, you go 7 over 1 is 7. 6 over 2 is 3 times 7, 21. Okay. And so you just, you just keep doing the multiplying by that ratio. Okay. Okay, so that's how you can compute those relatively quickly. Okay, so 7. Only got 10 minutes late. You overlaying the triangle over the equation. That is correct. So remember the coefficients in the binomial expansion are the coefficients in Pascal's triangle. They are the same as the binomial coefficients. Okay, so let me do 7, which is r times r minus 1 times NCR is equal to n minus 1, n minus 2, CR minus 2. This is for r between 2 and n. And again, r and n are natural numbers. Yes, this is the 7th rule. Okay, so let's prove this. Okay, so this is r times r minus 1 times NCR. So r minus 1. NCR is n factorial over r factorial n minus r factorial. So this is equal to r minus 1 times n minus 1 times n minus 2 factorial. R factorial is r times r minus 1 times r minus 2 factorial. N minus r is the same as if I subtract 2 from both n and r, I'll get the same difference. So again, differences are translation invariant, so I can just move them and they'll be the same amount. Notice that the r minus 1's cancel. Let me write n minus 1 out in front. So I get n minus 2 factorial over r minus 2 factorial times n minus 2 minus r minus 2 factorial. And so this is n minus 2. By definition, this is n minus 2 CR minus 2. So I'm done. Yes, you do. Okay, so property number 8. Actually, maybe I should tell you this. Give you some notation first. And so, NCR is equal to n factorial over r factorial n minus r factorial. NPK is equal to n factorial over n minus r factorial. So this is really NPR over r factorial, which actually is my second definition that I gave for the binomial coefficient. Okay. C, because they're called combinations. P, because they're called permutations. Let me do property number 8, which says RPK times NC, okay, 1 second, NCR is NPK times N minus K CR minus K, where I'm going to have 0 less than or equal to K less than or equal to R less than or equal to N, and where K, R, and N are natural numbers. Okay. Let's do this proof. Okay, so RPK times NCR. Well, this is equal to, by definition, and so by definition, this is n factorial over. Oh my goodness. Uh, okay, so for the captioner, this is probably going to be another about 10 minutes. Okay? Okay, so you can leave if you need to leave for the captioner. Okay, so RPK, by definition, yes, RPK is R factorial over R minus K factorial. Just by definition of RPK. And NCR from above is n factorial over R factorial n minus R factorial. Okay? And so this is equal to the R factorials are going to cancel. So this is R minus K factorial times n factorial n minus R factorial. Okay, so basically now I'll just sort of put what I need. And so NPK is, well, that's n factorial over n minus k factorial. Okay, so that means that above I've got to have n minus k factorial. So I've done nothing. I've just multiplied and divided by the n minus k's. That first term gives me the NPK term. And now I'm almost done. This is n factorial over n minus k factorial times n minus k factorial over r minus k factorial times. Now, since differences are translation invariant, I can subtract k from both n and r and still get the same difference. But if I look, this is just npk, and this last term I just wrote is n minus k cr minus k. And so I am done. Okay. Unfortunately, I can't give you examples because I only have 10 minutes left. Let me do problem number 9. Property number 9. There are many, many examples for this. Matter of fact, you'll probably have, if you take statistics, you'll have a half a semester of them. If you take, you know, pre-calculus, you'll have another half semester of them. So that there's just too many for me to go over. Okay, so let's do property 9. So let's say I equaling 0 to k of a ck b k minus I this is equal to a plus b ck. Okay. No, this is property 9. Okay, so proof. The previous one was property 8. So this is 9. So let's show this. So first, let me look at 1 plus x to the a, 1 plus x to the b by the binomial theorem. Oh, which I'll prove I should have proved that is 9. Maybe actually I'll do that instead, since this uses. Okay, so let me do this. Let me do this as 9, and this will be 10. That one I just wrote will be 10. So let me show this, that x plus y to the n is equal to the sum k equaling 0 to the n in C. Oh, let's use an R. No, let's use k because my R's look like K's. In C k, x to the n minus k, y to the k. Of course, this is true when x is 0 and y is 0. Or when x is 0 or y is 0. So let's just assume x is not 0 and y is not 0. When x is 0 and y is 0, or y is 0, you have to use some weird definitions for 0 to the 0 so that everything works. So let's use mathematical induction to prove this. Yes, unfortunately, I have 5 minutes left. Okay, so let's use mathematical induction to prove this. So let's do the initial case. So the initial case is, well, let's look at what is x plus y to the 0. That's just equal to 1. And let's look at the sum k equaling 0 to 0 of 0 ck x to the 0 minus k y to the 0. That's just equal to, well, there's only one term, 0, 0, x to the 0, y to the 0. Well, 0 c0 is 1. X to the 0, y to the 0 is also 1. Again, I'm assuming that x and y are not 0. Or otherwise, just use some weird definition of 0 to the 0 equaling 1 to make this work. Okay, so therefore, I've shown the initial case, because that means that this is, by the above, x plus y to the 0. Okay, so I've shown the initial case. Let's do the induction case. And so, for the induction case, let me assume that the sum that x plus y to the n is equal to the sum k equaling 0 to the n in ck x to the n minus k y to the k. Then x plus y to the n plus 1 is equal to x plus y times x plus y to the n. And so, this is the 9th rule that I'm giving you. Okay. And so this is equal to x plus y times, well, x plus y to the n, we've assumed is the sum k equaling 0 to n of nck x to the n minus k y to the k. And so let's just multiply x inside the parentheses and y inside the parentheses. So if I do that, this is the sum, k equaling 0 to n of nck x to the power n plus 1 minus k y to the k plus sum k equaling 0 to n nck x to the n minus k y to the k plus 1. Just multiplying x and then y inside the summation. Okay. And so let's just write out the first term here. So that's nc0, but I know that's 1 to the power n plus 1 plus, well, the rest of these terms, k equaling 1 to n of nck x to the n plus 1 minus k y to the k plus, let's write out the first k term, the first n terms here. So k equaling 0 to n minus 1 of nck x to the n minus k y to the k plus 1 plus the very last term. And so the nth term is ncn, which is 1. N minus n is 0, x to the 0 is 1, times y to the n plus 1. So this is equal to, well, x to the n plus 1 plus. For this term here, I'm going to let, let's say r equal k minus 1. Yes, this is telling us the binomial theorem, okay, how to do this expansion. Okay, so this is equal to, so let k equal r minus 1. I'm sorry, so r is equal to k Okay, so I'm trying to show that if you assume that this is true for n, then this is going to be true for n plus 1. Okay, so that's what I'm trying to prove. Okay, so r here. Oops, sorry about that. So when r is 0, when r is 0, k is 1. When r is n minus 1, k is n. And so this is k. So this is r plus 1. X to the n plus 1 minus. Oh, I see. I should have plugged that with there. Okay, so wait 1 second. Let me rewrite this. Sorry about that. So let me rewrite this as the sum, k equals 1 to n of nck x to the n minus k minus 1 y to the k plus sum k equals 0 to n minus 1 nck x to the OIC n plus 1 minus k, and this should be n plus 1 minus k plus 1 y to the k plus 1 plus y to the n plus 1. So for the second term, I just wrote n minus k is n plus 1 minus k plus 1. Okay, so this is equal to x to the n plus 1 plus sum k equals 1 to n. Oh, and I guess in this case, I'm going to just call this, instead of k, I'll call this r. So I'll call it r. So I'll call this NCR. N plus 1 minus r, y to the r, plus, in this term, I'll call k plus 1 r. So I'll let r equals k plus 1. So let's do that. So this is the sum. When k is 0, r is 1. When k is n minus 1, r is n. And k is r minus 1. K plus 1 is just r. K plus 1 is just r. So now notice the following. These two terms start and end at the same values. They have the upper and lower limits the same. The variable parts are the same. Therefore, I can write this as x to the n plus 1 plus sum r equaling 1 to n of NCR plus NCR minus 1 x to the n plus 1 minus r y to the n plus y to the r 1 second plus y to the n plus 1. Okay, so this will be again, look at the sample final exam to figure out what's on the final. Remember, I told you that a few minutes ago. So if you want to figure out what's on the final, look at the sample final exam. Okay, so this is equal to x to the n plus 1 plus sum r equaling 1 to n. But notice that this, by property, there it is, 4, is equal to, so using property 4, n plus 1 CR x to the n plus 1 minus r y to the r plus y to the n plus r. But this is just the sum r equaling 0 to n plus 1 of n plus 1 CR x to the n plus 1 minus r y to the r. And so that's what we wanted to show. So again, look at the sample exam. The problems on the sample exam are the problems that you'll be getting on the exam. Okay, so therefore, so I've shown the induction step, so therefore, by the principle of mathematical induction, we have that x plus y to the n is equal to the sum, I don't know, r equaling 0 to n of NCR, x to the n minus r, y to the r, for all n being whole numbers. And I am done. So it was to prove the binomial theorem. And so this proved the binomial theorem. And lastly, let's do the very last one. Property number 10, which is the sum I equals 0 to k of a c I b c k minus I, that's equal to a plus b c k. Okay, so let me prove this. 1 plus x to the a, 1 plus x to the b, well, by the above binomial theorem, is just equal to the sum I equaling 0 to a of a c I 1 to the a minus I x to the a times the sum, let's say j equaling 0 to b, bcj 1 to the b minus j x to the j. This is equal to sum I equaling 0 to a of ai x a, sum j equaling 0 to b bcj x to the j. Since 1 to any power is just that, is just 1. This is equal to sum I equaling 0 to a, sum j equaling 0 to b of I a c I b c j x to the, why did I write that? X to the I plus j. So let k equal I plus j. So then this is equal to sum k equaling 0 to a plus b, sum I equaling 0 to k of a c I b c, j is just equal to k minus I, since I plus j is equal to k, times x to the k. What is I? I is your dummy index. I is a number going from 0 to k. Also, we have the following. I know that 1 plus x to the a, 1 plus x to the b. Since I have the same base, I add exponents. And so by the binomial theorem, I'm almost done. By the binomial theorem, this is equal to the sum. And let's do it with a k. Equaling 0 to a plus b of a plus b ck, 1 to the a plus b minus k times x to the k. But this is equal to the sum, k equaling 0 to a plus b of a plus b ck. 1 to any power is just 1, x to the k. But notice that I have the sum, k equaling 0 to a plus b of some stuff, x to the k, k equaling 0 to a plus b of some stuff, x to the k, and these quantities are the same since they both came from the same expansion. Therefore, the sum, I equaling 0 to k of a, I, b, k minus I is a plus b c k. And that is your answer. And I am done. Okay, so that is it. Okay, so I can let the captioner go. And so that was it. That finishes off all the properties of Pascal's triangle. And so Monday, please turn in these notes to obtain full credit and so there are these 2 extra credit sessions that we've had. Plus, please turn in the group work that I told you from yesterday. Turn those in on Monday, and we'll have exam number 5 on Monday. What is a formula? A formula is a literal expression. It is something where you relate variables to other variables. So usually it's one variable related to another variable. Okay? So they have a whole bunch of unknowns related to in some relationship. That's a formula. Okay? So that's it for today.